Okay, this is Chapter 5, Part 2, and we're going to pick up where we left off on this slide. Important things to note in this slide is this first bullet point, is that the variations in the gravitational force result in changes in the acceleration due to gravity. Remember, acceleration due to gravity is our lowercase g. Now, g is pretty constant near the Earth's surface. Once the distance increases, g is going to have some slight fluctuations. Now, keep in mind that g is not strictly constant from place to place. In order for it to be constant from place to place, the Earth would have to be composed of spherical shells, with each one being uniform. We know that's not the case. Because there is a slight variation, we can use the measurements of g to help us locate underground ore deposits. So geologists use this to help them in their work finding these ore deposits. Another thing Newton's work has helped us is to predict the orbit of artificial satellites that orbit the Earth. So we can do this by knowing that the force changes with distance from the Earth. We know what acceleration is and the orbital characteristics. So we can know these things at different, what to expect at different altitudes. The higher the satellite is in the orbit, the longer it takes to complete one orbit. If we had a situation where our satellite was positioned directly above the equator, it would appear that it would be fixed on one spot in the Earth or on the Earth, and that would be what's called a geosynchronous orbit. Now, so we want to be able to write some expressions, okay? So we want to write an expression for centripetal force that's required to maintain a satellite in a circular orbit of radius r. So we know this formula, force is mass times acceleration. We know this formula, centripetal acceleration, is v squared over r. So now what we're going to do, we're going to substitute centripetal acceleration into this force is mass times acceleration. And when we do that, we get this formula. Force equals mv squared over r. Now, we've talked about gravitational force, and we know we have this formula. Force is capital G, m, in this case our m2 would be the mass of the Earth, over r squared. So what we can do is we can set the two forces equal. So by the two forces, I mean this force and this force. So we'll put a 1, we'll put a 2. So we come over here, and this would be our 1, and this would be our 2. They're both forces, so we set them equal. We rearrange this equation, and we solve for v squared. And that gives us this equation that you see right here. So what this shows us is that all satellites with this orbital radius have to have the speed. Once we know the speed, we can calculate the period. Period being time, so we have period equals c over v. We substitute what c is, which is the circumference of the circle, and we get t equals 2 pi r over v. We could also get an expression for period by substituting what v is into the period equation, and we come up with this equation, that period equals 2 pi times the square root of r cubed over g times the mass of the Earth. Okay. Now this equation doesn't contain the mass of the satellite, so therefore all the satellites orbiting the same central body obey the relationship. This expression right here is Kepler's third law. T squared equals KR cubed. Now, K is a constant, and K equals 2.97 times 10 to the minus 19 seconds squared over meters cubed. So what this is showing us is that the period increases as your orbital radius increases. Okay, let's try a few problems with satellites. This first one, we have a satellite being sent to the universe for remote sensing. You're asked to calculate the orbital velocity of Earth. So we know we're looking for orbital velocity of Earth so that the satellite revolves around the Earth if we're given the radius to be 6.57 times 10 to the 6 meters, and we're given the mass of the Earth to be 5.98 times 10 to the 24th kilograms. So we look at our formula sheet, and we see our formula is V squared equal capital G, mass of the Earth, over the radius. We want to rearrange this for V, and all we have to do is take the square root of both sides. So therefore we get V is going to be the square root of capital G ME over R. So V is going to be the square root of G, 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared. Multiplying that by mass of the Earth is 5.98 times 10 to the 24 kilograms, dividing it by R, which we're given to be 6.57 times 10 to the 6 meters. And when we plug this into our calculator, you should find that V equals 7.8 times 10 to the 3 meters per second. Okay, our next problem, we have a satellite that is located at a radius of 7.28 times 10 to the 6 meters above the Earth's surface. You're asked for the period, and you're also given the mass of the Earth. So we know period is T, so where T is going to be 2 pi times the square root of R cubed over G times the mass of the Earth. So therefore T is going to equal 2 pi times the square root of our radius, which we're given to be 7.28 times 10 to the 6 meters, and that has to be cubed, divided by G, which is 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared, times the mass of the Earth, which we're given to be 5.98 times 10 to the 24th kilograms. So we take the square root of that, multiply that by 2 pi, and we get T equals 6.179 seconds. Okay, let's try one other one. Now, in this one, you're looking for how far above the Earth's surface. So we're basically looking for H. So let me give you the formula for H, because it's not on your formula sheet, so you might want to add this. H equals R minus R of the Earth. Okay? So we're looking for how far above the surface, in this case, what is H, must a satellite be located if it's to circle the Earth in a time of 28 hours. So our period is 28 hours. Now we know we have to convert that to seconds. So we know we have 60 minutes in 1 hour, and we know we have 60 seconds in 1 minute. So that's going to give us 1.01 times 10 to the 5th seconds. Okay. We know from previous problems what are other variables that we need to solve this problem. So let's look at our formula we need. Well, we have our formula that tells us T equals 2 pi times the square root of r cubed over g times the mass of the Earth. Okay. Well, we know the radius of the Earth, but we got to solve and find out which this r is, which is this r right here, this r cubed. Okay. So we actually need to solve this equation for this r cubed. Okay, so let's do some rearranging. So the first thing, we want to get rid of this 2 pi. So let's divide out 2 pi by both sides. Okay, and then that's going to leave us T over 2 pi equals the square root of r cubed over g times the mass of the Earth. And then what we're going to do is we're going to square both sides, and that's going to leave us T over 2 pi squared equals r cubed over g times the mass of the Earth. And then we're going to multiply g times the mass of the Earth by both sides. Okay, so that'll cancel, so we're going to be left with r cubed equals T over 2 pi, that's all squared, times g times the mass of the Earth. Okay, so let's fill in the blanks. So r cubed is going to equal g times the mass of the Earth, so we have 6.67 times 10 to the minus 11 newtons meters squared kilograms squared times the mass of the Earth from a previous problem we know is 5.98 times 10 to the 24 kilograms. We're multiplying it by our period, which we converted 1.01 times 10 to the 5th seconds. Divided that by 2 pi, and that's all squared. So we wind up with r cubed equals 1.03 times 10 to the 23 meters cubed. When you take the cubed root of that, then r is going to equal 4.69 times 10 to the 7 meters. Now you will probably have to look in your calculator book or Google your specific calculator type if you don't know how to do the cubed root on your calculator. So this is r. Now we can figure out h. So h is going to be r, which is 4.69 times 10 to the 7 meters, minus the radius of the Earth, which is 6.57 times 10 to the 6 meters, and that's going to give us h to equal 4.03 times 10 to the 7 meters. Okay, this ends part 2. In a couple minutes, I will start part 3.